Well, it looks like we are live on another CNBT 1311 video. This will be Chapter 3, Video 1. Chapter 3, Foundation Systems, has 24 pages, it looks like. 25. Let's see what we can get through. We'll see if we can make this as painless as possible. Now, again, I'm a structural engineer, a former civil, structural, and mechanical engineer. And this is not a structural engineering course, nor is it a soils mechanics course. The foundation, according to Ching, and since that is our book, the foundation is the lowest division of a building. Well, okay, fine. It's the substructure. So we would call this the substructure, or Ching does. I call it the foundation. The foundation is the substructure. And the foundation is what the substructure sits on. It's all a part of the foundation. In this diagram, we have the retaining wall. Why? Because it is soil compacted against it and supporting soil or rock. We have active pressure, soil pressure on this. So we have a lot of different forces going on. This says anchorage required to resist sliding, uplift, and overturning. Well, no kidding. That's what the whole idea behind a foundation is. But anyway, all right. I'm not making fun of Ching. All right. It's a good book. It really is. Its primary function is to support and anchor the superstructure. So, for the sake of this discussion, what's above the substructure is the superstructure. Then we have the substructure, which sets on the foundation. Now, me, as an engineer, the substructure is the foundation. It's all a part of it. I am not going to make a substructure separate from the foundation. But potato, potato. We'll move on. All right. The principal loads on a foundation are the combination of dead and live loads acting vertically on the substructure. In addition, we already know that we have earthquake and wind loads, right? You got wind loads, you got earthquake loads that come in all different forms, side shake, vibrations which set up the frequency curve up through the building and all that good stuff, right? Okay, all right. Let's move on. Passive earth pressure. Now, what does that mean by passive? That just means that's the weight of the soil. And as we have described before, the soil, the weight gets heavier down here because there's more weight, there's more soil. Now, if we get a lot of rain and the soil gets wet, we got water in the soil, and the pressure becomes greater. All right. Thrust from anchored or tensile structures. We've already discussed this more than we probably want to take on. And what is this? That's called a buttress, right? Yeah. Where that force on the arch or the tensile structure or whatever, it's still a buttress. I don't care what anybody else calls it. All right. We have some shear resistance from heavy wind load. All right. So this is wind. Oh my goodness. I need a different mouse. Wind, okay, uniform pressure, but we also know that the wind pressure is not uniform like that. Wind actually acts just like soil pressure, right? Except it's in reverse. It's like this. Because the higher up you get, there's less thing to block the wind, especially in a highly populated area. We have a building over here. This wind's going to hit that building and then come up here. So the higher, the taller the building, the more the wind load is at the top. So it's just the opposite. It's just the opposite of the soil load. So don't be surprised if your engineer goes, hey, our wind loading looks like this. because down here would be low pressure, right? If this wind is coming over the building and hitting that, what's going to happen down here? This is going to be low pressure, and this is going to be high pressure. All right? So your mileage may vary, but that's why you hire engineers. Okay? All right. And then, of course, this building's going to want to go that way, and then the foundation is going to want to slide that way, and the resistance of it's got to go that way, so we can stay in what? We can stay in equilibrium. All right, because we don't want the stuff to move, right? All right. Okay, settlement. Settlement's a big problem. We go down here and we excavate for a substructure and then the foundation, or the foundation, which includes the substructure and the foundation. All right. But before you start building this, if we excavate, we come down here and we take soil samples, not for the soils report, but we do soil density test. We do nuclear soil density test to make sure that this soil is compacted to the ultimate density that our soils engineers tells us it needs to be before we start laying the foundation. Now, as we remove the soil from this area. We remove the soil from this area. Then it's not uncommon for the soil underneath it, when we remove this weight, that it to bounce up a little bit. It moves up, expands a little bit. And then we come down here and we start compacting this soil and get it down to the elevation that we want. For the foundation, our construction engineers, they shoot elevation and we get it compacted. Then we start laying in the concrete. Once the concrete's laid in, then we start benching the backfill. And we use heavy compacting equipment, rollers, compactors to compact this soil, and and sometimes the compaction force is much greater than what would be the passive force of the soil once it gets put back in place. So your engineer has to design the wall for the construction forces against this as the stuff's being compacted. Okay, but settlement is the gradual subsiding of a structure as the soil beneath its foundation consolidates under loading. And theoretically, everything will subside a little bit. Some settlement is to be expected, and it is to be expected, and you take that into account in your design. Recalls an induction volume of soils, air, water. This consolidation is usually slight and occurs rather quickly as loads are applied. If you compacted this subgrade before you started laying in your foundation, okay, was it moist? What was the water density? What was the moisture content, etc.? A properly designed and constructed foundation system should distribute its loads so that whatever settlement occurs is minimal, or it's uniformly distributed across the structure. Now, we're not talking feet, okay? We're talking fractions of an inch, if at all right? Now, remember what I told you. Down here in this area, soil is on the average 150 pounds a cubic foot. Reinforced concrete weighs 150 pounds a cubic foot. So what we're pulling out, we're putting back. So that helps us stay in equilibrium. The problem that you have is if you're in a condition of differential settlement. The definition of differential settlement is that, okay? The definition of settlement is this. Differential settlement you do not want, okay? One side of your building will settle down greater than the other side, leaving you with an out of square structure and a lot of structural stresses that you didn't account for. Your soils engineer and your structural engineer are the ones to keep you out of this trouble. All right. The foundation and the foundation design and the soils analysis and the soils engineering is highly, highly important in any construction project, even a residential structure. You come out here on the Katy Prairie where you have a highly silica-sided soil, means it expands a lot. Don't expect your slab on grade. You're just coming out here and digging some grade beams and putting the house up to stay settled evenly over its life cycle, unless you happen to be in the middle of a uniform body of soil. But you have no control over that. You may have highly silica-sided soil on this side of your slab, and then it comes over here more of sandy loam because this is an old creek bed. They got filled in years ago, and the developer filled it in, and he didn't compact it worth a darn. Okay? So then your builder comes in, and he tries to make up for it with some sand, but you know he doesn't compact it all that well. And so now you've spent $300,000 on a house that may or may not uniformly settle. And it makes homeowners very upset, and it gives all these foundation people that advertise around here all kinds of extra money. There's reinforcing steel. To try to jack your slab up. And a lot of those guys are a bunch of shysters. And that's a whole nother conversation, which I really shouldn't even have gotten into. All right. Differential settlement can result in the failure of the structural integrity of a building. I've done a lot of forensic analysis, forensic engineering on structural failures, and a lot of them resulted from just this. One side of the foundation system failed, it's very expensive, if not almost sometimes impossible to fix. So let's look at the types of foundation systems. Foundations utilize a combination of bearing walls, columns, piers to transmit building loads directly to the earth. These structural elements can form various types of substructures. We have basements. Now, the best kind of a basement is a monolithic concrete wall that is monolithic. It's a giant concrete basin that's monolithically poured to a concrete slab with a water stop in there. So the walls come down, they meet a slab, there's a construction keyway, and a water stop barrier. This is the outside, this is where the soil is at. This is the inside, and all of this is poured as one contiguous unit. Okay? So basements are like a story, another story of your house below. We don't have too many basements down here. Why? Because of the water table. Crawl spaces are shallow, for lack of a better term, shallow areas underneath the house. If you've got a house that's on pier and beams, let's say these are piers, pier and beam foundation. There's the floor joist, and then the house is built up on those. And then you have an enclosure for the crawl space, usually on a small footing, and it's a small area underneath the house. A lot of houses in the ancient days of yore were built like that. Our houses now are slab on grade, especially down here. Concrete slabs on grade, which is what we have here in this area. I do know a guy over in Rice Village that does have a genuine basement in his custom $3 million house. I asked him what he did for the water table, because the water table is about halfway up his basement wall. He spent a lot of money on waterproofing the outside walls of his basement. Tons of money. But this guy has tons of money. And what's in his basement? his basement is full of his wine collection. And that makes sense because it's a constant temperature. His basement stays at about 68 degrees Fahrenheit year-round. So 68 degrees F, which is a little warmer than some wine people. My wife is a master of wine, Wesset level 3, and I don't understand much about these wine expert stuff. But anyway, 68 degrees is about the maximum temperature they want to store their wine at. So anyway, he has his whole basement full of his highly expensive wine collection. Well, I digress. All right, so concrete slabs on grade, they're spread out uniformly. Okay, I drew one up here. And if they're done properly and the subgrade is handled properly, then the weight of the structure, the walls and any interior load-bearing walls on the grade beams uniformly spread the load across the slab. Unless, of course, you got a giant oak tree out here that you just had to save to, because your wife likes the oak tree, and these giant roots continue to grow under your slab and eventually start putting differential pressure on your slab, and you have upward movement on your slab, which is the same as settlement, except it's going in the opposite direction. Because here's a tree, okay? So the roots will push up on the slab, which is the same as settlement, it's just going upward instead of down. It's just as bad. So if you're going to design a house near a tree, you need to get with a good tree expert and find out where those roots are. Dig a trench, cut those minor roots, and put a root wall in between the house slab and the tree. And then put irrigation out here so that you can water it with good old H2O. So those roots will go to the water and away from your slab. Not everything's that simple. So, all right. So everything, the roof, the floors, the walls, the windows, the people, the loading, everything goes down to the foundation. Now, sometimes, and I know some people who have built houses down here in this crummy soil that we have, that they have actually spent a lot of money having piers put down. They get a soils analysis, an actual real soils analysis, and they go down about 12 feet to the clay level, which is not affected by our drought, and they put drilled piers in. They don't put spread footings like this. They'll go down and they'll have drilled piers. They'll drill down, and then the bottom is belled out with bottom. Again, that when the final drill spins, it hogs out a bell, and then they fill this with concrete. And then the slab is then poured on top of the drilled piers. And it's supported on these piers, and there is a space underneath the slab. They usually use crush boxes, which are core boxes that holds up the water and the concrete while this is being poured. And over the life cycle, these things rot out, and if the soil does expand, it expands up into this void space and doesn't affect the slab. And the slab is supported on these, not square, but they be supported on round piers with a round bell bottom. Pretty poor drawing, but that's what happens, and that have to go all the way around. There we go. All right. Okay. So that's a bell bottom pier. You may have seen some of the drilling trucks driving around that have that. The actual bell section looks like a big giant can. They hook to the drill stem. The drill stem is an auger. Then they take the auger bit off, and then they hook the can on it with the drive shaft for the drill. And inside here is a centrifugal set of blades, two of them. And when they spin it, these blades sling out due to the centrifugal force, and they cut the bell at the bottom. They stop spinning it, the blades come in, they pull it out, then they dump rebar in there, a can, a rebar, and fill it with concrete. Types of foundations. You have shallow foundations. Now, Ching defines a shallow foundation or spread footings are employed when stable soil of adequate bearing capacity occurs relatively near the ground surface. They're placed directly below the lowest part of a substructure and transfer building loads. Okay, so these would be shallow. Now, this poor person that owns this building, assuming this was one building on the same site, it has good bearing on this side. I've never seen a soils analysis that had a direct demarcation line like that. But let's say for some reason this was an old bayou or something that filled in by some sneaky developer, and we had some really nasty soil over here. This is good soil and this is bad soil. So in this case, they had to go down with a different foundation on this half of the building. Let's just assume this is the same building, okay? And so you have to come down and go through all this garbage with something that'll support the building load. And in this case, it looks like they used cast-in-place piles. So you dig out all this nasty dirt, come in with some good stuff and compact it really good, put in these footings, but before the footings, you'd come down with drilled piers and then cast the footings on them, okay? So they extend down through unsuitable soil. Don't be surprised if that happens. Underpinning, okay? Ching defines underpinning as the process of rebuilding or strengthening the foundation of an existing building. Now, this is what happens when a building starts to have differential settlement. You have to dig down, put in columns and piers. There are companies that makes lots of money selling their product, okay? And they put jacks underneath here and shim it and try to level the building back. It's extremely expensive. The buildings get cracked a lot when they do that, and sometimes it works and sometimes it doesn't. You have to provide a temporary support while an existing foundation is repaired, strengthened, or deepened. Needle beams are passed through the foundation wall and carried by hydraulic jacks and shores, and that's what these are here. These jacks, they jack the building back up, or try to jack it back up. Then they come in here and shim all of this, and sometimes they get lucky and they can pump high pressure concrete in here. Sometimes they can't. The best thing is to avoid this. Just avoid it if you can. But don't be surprised if you go to work for somebody and that's what they do for a living. They go fix buildings that weren't designed right in the first place. Or they had a soils issue that no one caught up front. This kind of work is extremely expensive, very expensive. You want to avoid this at all cost, okay? That's what underpinning is. Another method for providing temporary support is to dig intermediate pits under the existing foundation down to the level of the new footings. After the new foundation wall and footing sections are placed, additional pits are dug until the wall has deepened. This is insane, in my opinion. This doesn't work down here. You do more damage to the existing structure. It's extremely expensive. The best thing to do is to avoid it at all possible costs. An alternative to extending a new foundation wall and placing new footings is to construct piles or casings on either side of the existing foundation remove a section of the foundation wall and reinforce a concrete pile cap. Try to pin this with an external concrete slab. Now, in order to do this, you got to dig down here, and you got to dig underneath this slab. You have to. I don't care what the guy who's selling this to you says. All this crap has to be removed to get in here to drill this. Now, how are you going to drill this under an existing slab? Well, if this is big enough, you can bring in a small bobcat with a drill and start drilling this shaft. Okay. Again, that means you got to break this concrete out, drill down through here, then you got to get underneath all of this after you've removed it, form and cast this, and try to pin this new concrete to the existing wall. Very, very expensive. And then you got to repair all the work you did. Now, the big question is, and some of y'all have probably already thought about it, well, compacting all this dirt back in here is one thing. How in the name of Zeus do you get underneath an existing slab and compact this? Well, irrespective of what these contractors tell you, you really can't. You can crawl these little guys back in there with pneumatic rams and try to compact all this stuff as best you can, but you'll never get it as compacted as it was in the beginning. The best thing to do is to avoid this with good upfront foundation engineering. All right. I love this. When the building site is sufficiently large, this kind of goes back to our site planning and orienting the building in the utopian manner, right? That the sides of an excavation can be bench terraced or sloped at an angle less than the angle of repose. What that means is you're digging a pit that's benched. This is a bench down to where you're going to put your foundation. Wow, that's a nasty looking foundation, isn't it? Okay, there we go. Well, that's still nasty. Well, whatever. You get the idea. These are what's called an excavation bench. All right. And then all this has to be backfilled and compacted. Money. All right. Terraced or sloped at an angle less than the angle of repose. You just can't dig an angle if this stuff's going to slough back off in there. Plus, you got to be able to get down here and put the formwork in, right? And then you got to get the formwork for this, assuming it's a wall. All right. So it must be temporarily braced or shored. Okay. So if you can't bench it, then you've got to do shoring. And this is what shoring looks like. All right. Now, you can do it with sheet piling, which are interlocking sheets that don't really give you a good detail here. But a sheet pile looks something like this. And they lock in place. And they're driven by vibratory or pneumatic or a hammer. All right. So soldier piles are these H-beams that are driven into the ground, and then you put lagging. This is what's called lagging. You slide that down against the face of the shoulder piles, and that holds back your excavation wall. Sheet piling is more prevalent for that kind of work down here, because at the top of these have a little hole in them, and then that's how they extract the sheet pile. When they're done, they'll vibrate it back out. Let's see. Sheet piling consists of timber, steel, or precast concrete. Most of your sheet piling, you'll see it down here for pits, are these interlocking sheet piles. And sometimes they'll just leave them in place and pour concrete up against them. Especially like, let's assume this is the property line. Okay, that property line. This is not your property, it's someone else's up here. They'll drive the sheet piling along the property line. They'll excavate out this side. They'll come in and pressure wash all the dirt away. And then if they're going to put a foundation wall, they'll form up one half of the wall. This would be the forming, and this would be the reinforcing steel. And they would just pour the concrete in here, and that would be the reinforced retaining wall or the foundation wall. All right, tie backs. We talked about this before with retaining walls. Sometimes the tie backs are just drilled and they're pressure grouted. It's giant screws in the dirt. Okay, it may be used for cross spacing or rakers for a temporary wall. Okay, but again, by the time you do all of this, this is expensive. It may be more cost effective just to drive a sheet pile wall around your excavation. Drive it around your excavation down to the depth that you need, and excavate all the dirt out of this, and then do your construction inside your caisson or your sheet pile box. All right. Now, sometimes you need to tie back your sheet piling if you can't cantilever it. If it's just driven in the ground like this, this would be a cantilevered sheet pile wall. Sometimes you do have to do tie backs. But if this is not your property, then you got to get clearance for these tie backs. And once they're in the ground, they can't really be removed. And then you got to worry about what? Utilities, gas lines, electrical lines, AT&T, telephone lines, all in these areas that you got to try to miss. All right. A slurry wall. A slurry wall is nothing but a wall that you make out of concrete. You drill a hole and you put in a continuous row of concrete piles. And sometimes they need to be tied back, sometimes not. Very expensive. Okay. Here's a term: slurry of bentonite in water to prevent the sidewalls from collapsing. Okay. They use bentonite, if I'm not mistaken, in the slurry walls for the World Trade Center years and years and years ago. Okay. Bentonite seals against water. But down here you'll see a lot of these walls made out of the sheet piling. All right. Now, we talked before about lowering the water table with a well point, and I don't remember if I actually used that term in that first couple of videos, but this is a well point system. All right, I told you about the straw that you stuff down, you drill down into the water table, and you hook pumps to it, you suck it out, and you draw the water table down. You draw down the water table. All right, this would be the existing water table, and while you're doing your construction, you draw it down. Okay, that's dewatering. This is called a well point system. Well point system. Well point. Ching doesn't use that term, but it's called a well point. Well point system. And they are not cheap. And then you got to figure out where you can dispose of the groundwater during the length of your construction. The idea is if you're going to put in, let's say, a deep foundation wall, once this water table gets drawn down, you got to get your soils engineers back in here and starts doing another soils analysis to make sure this the soil is dried out enough that you can start working. And then you come in here and put your foundation and start building your foundation walls up, or whatever you're going to do for your, what is this, substructure. Yeah, that's the term we'll use. All right, it's a pretty nasty looking substructure. And there's your superstructure starting there, okay? And then when you get all this stuff backfilled properly, and soil density has been checked to a 98% compaction, then you can theoretically stop your well point. But most of the well pointing doesn't stop then until they get the full structure up. Okay, the weight of the structure up. Because they don't want the water table to come back up here and try to turn this into a boat and float it. Much like a swimming pool, when you dewater one, if you don't have plugs in the bottom of the swimming pool, you run the risk of popping your pool up because of the water table. All right. Shallow foundations. The lowest part of a shallow foundation are spread footings. Now, I'm going to disagree a little bit because spread footings can be deep, okay? But we'll say that they're shallow. They're not going down hundreds of feet like they would in some nasty areas where you have to find bedrock because you're over a bunch of silt. Okay, but that's fine. As far as this course is concerned, the lowest part of the shallow foundation, we'll call them spread footings. All right. Don't be surprised if you go to work for somebody they disagree with that. Okay. They're extended laterally to distribute their load. Whether these spread footings are rectangular or they're round, like a bell-bottom footing, this would be the column coming up with reinforcing steel in it. And this is the bottom of the bell. Okay. All your spread footings generally come out at about a 45-degree angle. The load is spread out. Okay. And this is what we use as a rule of thumb for shear forces down the column going to a spread footing, whether they're square, rectilinear, or they're round. Okay. All right. What's he telling you here? Oh, okay. All right. This distance is the diameter, D for unit masonry, D for concrete walls, and critical sections for shear. All right. Just go out to the outside of your column. But again, this is not a structural engineering course. And you draw a 45-degree line across here. Okay. That's for absolutely the minimum. Absolute minimum. You got to figure out what the surface area of this is and figure out what your bearing capacity of the soil is based on each column. All right. I'm not going to make you do calculations for this. Concrete having a minimum compressive strength of 2,500 psi at 28 days. I would fire you if that's what you expect. I want 5,000. I want 5K psi concrete. Pounds per square inch. 5,000 pounds per square inch of concrete strength at 28 days. This is like freaking Sackcrete that you buy at Home Depot. Okay, your average ready mix is 3,000 to 4,000 psi. That's at about $175 in today's cost per cubic yard. A couple of more sacks of cement in the mix will get you up to 5,000. Anyway, I digress. All right. Okay. Longitudinal temperature reinforcement in these footings. That's a rule of thumb. Depending on the loading and the soils analysis, you may need more than just minimum temperature steel. All right. You may need to actually put some heavy rebar in here. All right. But minimum is about 3% of the area. Okay, but again, that's not a part of this course. That's structural engineering. That's a part of that Air and Concrete Institute specifications for a structural engineer. All right. You want at least 3 inches for any buried concrete exposed to earth or water between the outside edge to the reinforcing. You want a minimum of 3 inches because you don't want the water to mitigate through here and start to rust the rebar. Okay. All right. Reinforcing steel. When footings for light frame construction bear on stable, uncohesive soil and transmit a continuous load of less than 2,000 pounds per linear foot, they may have the following cross-sections proportions. Again, your mileage is going to vary. Do not use this as a design requirement unless you're doing something for your farm. Okay? Get a soils analysis if you're doing something really important. All right, let's move on. To minimize the effects of ground heaving when groundwater freezes and expands in cold weather, building codes require that footings be placed below the depth of the frost penetration. We don't really have frost penetration down here. Your soils engineer, if you're working up north, will tell you what that frost line is on the average yearly cycle and where that footing needs to be. That's what you're paying them for. All right. Spread footings. Spread footings come in all kinds of shapes and sizes. I wouldn't say the most common forms of spread footings are strip, but Ching does, so that's fine. It depends on what part of the planet you're on. If it's a retaining wall, then yeah. If it's going to be an excavated wall, then yeah, the footing will be a spread footing. They'll cast the footing first, then they'll pour the wall on top of it with the water stop in there if it's going to be buried. Other types of spread footings include the following. This is a continuous footing. It's a reinforced concrete slab that the column's set on. A grade beam is a grade beam, okay? Some grade beams will set on a footing, some will not, depending on the design by your structural engineer based on the soils mechanics and the soils report. All right. A cantilevered or stripped or strap footing consists of a column footing connected to a tie beam. Now, you'll find this if you've got something that needs to be supported away from your main wall. Okay? Sometime in industrial factories, you'll have a column that sticks out where a crane needs to come out of the building or something, and this needs to support the end of the overhead crane or an overhang. Don't be surprised if your engineer wants you to has to have something like this. You're the architect. If you design it, think about it. If this is going to be the main wall for your main building, this is the foundation. This is a substructure, and the superstructure is going to go up from here. And this is a foundation. This would be a substructure column. And so something is pushing down on this column from up above. I mean, it could be something as, an overhang in a building that the architect wanted. I don't know. Who knows? Something like that. Okay. And then the cars can go park in here and drop off passengers. Who knows? All right. Here's another cantilever strap footing. And why do we call it cantilevered footing? Because it extends out from the main footing. But it's not truly cantilevered because it's supported by the soil, and it will be designed based on the soil bearing. A mat or raft foundation. Now these are kind of weird. It's a thick, heavy reinforced concrete slabs that serves as a single monolithic footing for a number of columns. So for some reason you might need a mat. Okay. I've never done a mat footing. Anytime we've done anything that was resembling a mat footing, we were able to come down with something like this with a big slab underneath it, and the columns could come up and then support the superstructure. But this is an example of a mat or a raft foundation. Okay. Mat foundations are used when the allowable bearing capacity of a foundation soil is low relative to building loads and the interior column footage becomes so large that it becomes more economical to merge them into a single mat. Anytime that we've done anything that needed something like this, we just flipped it upside down. And these beams were underneath this, and it was a reverse mat. So we didn't call it a mat footing. We just called it a foundational footing with grade beams underneath it that corresponded to the column line all the way across. Basically, it's like a waffle. It's upside down. And the top part of the waffle's flat. Floating foundation is used in yielding soil, has for its footing a mat placed deep enough that the weight of the excavated soil is equal to or greater than the weight of the construction supported. Again, this is balancing out the forces of what you pulled out with what you put in. In some cases, you might need something like this. Again, that goes back to your soil engineer and your structural engineer. This is foundation walls. Where are we at time-wise? We're at 46 minutes. Why don't we start this as video 2 and foundation walls. And this is a small smattering of foundations, footings and such. Okay. Don't be surprised if your engineer comes up with some other thing that's not in the Ching book. All right. Well, all right. We'll see you on the next video.